Welcome to SynthCosmos. For 2 years, we watched AI learn to think, writing code, generating art, passing the bar exam, but thinking was just phase 1. January 2026 marks a shift. AI isn't just in the cloud anymore, it's walking among us. The era of physical AI has begun. Right now, humanoid robots are being tested in homes across California and Norway. They're folding laundry, unloading dishwashers, and learning to navigate staircases. This isn't science fiction. It's happening in beta programs today. But here's what the headlines won't tell you. Behind every smooth demo is a brutal engineering war. Battery chemistry, neural network training, mechanical failures, and a single question that terrifies every company in this race. What happens when robots become cheaper than workers? Today, we're breaking down the 3 companies leading this revolution, the breakthrough that made it possible, and the economic shockwave that's about to hit. Let's begin. Three companies are defining 2026's humanoid robot landscape. Each has taken a radically different approach, and understanding these differences tells you everything about where this technology is headed. First, 1X and their robot, Neo. 1X is a Norwegian startup backed by OpenAI, and their philosophy is simple. Robots should be safe enough to live with humans. Neo doesn't look like a machine from a sci-fi movie. It has soft exteriors, rounded edges, and movements that are deliberately gentle. The outer shell uses compliant materials that can absorb impacts, which means if Neo accidentally bumps into your toddler, it's more like being nudged by a person than hit by a machine. In January 2026, 1X began delivering Neo units to select homes in Norway and California. We're talking about real families, not engineers, not beta testers with technical backgrounds, just regular people living with a robot in their kitchen. The deployment is small, maybe a few dozen units, but it's real. Neo can't do everything yet. It moves slowly, it sometimes struggles with complex tasks, but it can fold your laundry, hand you items from across the room, and navigate around pets and furniture. This is the first company betting that the home market comes before the industrial market. Second, Boston Dynamics and Electric Atlas. If 1X is going for your living room, Boston Dynamics is going for the factory floor. They've spent 2 decades building the world's most advanced robots. You've seen the videos of their machines doing backflips and parkour. But here's what changed in 2025. They retired the hydraulic Atlas. The old Atlas was a marvel of engineering, but it had a fatal flaw: hydraulic fluid. Under pressure, hoses would leak, seals would fail, and maintenance costs were astronomical. You can't have a $150,000 robot that needs a specialized technician every few weeks. The new Electric Atlas, launched in late 2025, is all motors and batteries. No fluids, no leaks. And it's designed for endurance. 10-hour factory shifts doing repetitive, precise tasks. Think automotive assembly lines where Atlas can lift 25-pound components, position them within a millimeter of accuracy, and do it 500 times a day without breaking. Boston Dynamics isn't aiming for your home. They're aiming to replace the 2.7 million people working in U.S. manufacturing alone. Third, Tesla Optimus. Elon Musk has been promising humanoid robots since 2021, and for years it looked like vaporware. But something shifted in 2025. Tesla stopped doing flashy stage demos and started showing Optimus working inside their own factories. Not perfectly, but working. Picking up battery cells, moving parts between stations, performing quality inspections. By the end of 2026, Tesla plans to have thousands of Optimus units working inside their Gigafactories, not sold to customers, not leased to other companies, working for Tesla. And this is the strategy. Perfect it internally where you control every variable, then scale it externally once the economics are undeniable. Musk has said the goal is to produce Optimus at a cost of $10,000 to $20,000 per unit, roughly the price of a car, and sell it maybe for $30,000. If Tesla can hit that price point with even 80% reliability, they're not just selling robots, they're selling a new form of labor that never sleeps, never strikes, and never quits. So you have three visions. 1X wants to be your helper. Boston Dynamics wants to be your co-worker in heavy industry. Tesla wants to replace entire workforces at scale. And all three are betting on the same technological breakthrough that made 2026 possible. So how did we get here so fast? Why are 2026 robots suddenly capable of things that seemed impossible just 2 years ago? The answer is a fundamental shift in how we teach machines to move. The old way of robotics was brutally precise and tragically brittle. Engineers would write millions of lines of code defining every single movement. Pick up cup, rotate wrist 23 degrees, close gripper at 40% force, move arm along trajectory XYZ. If everything was exactly where the code expected, perfect lighting, object in the exact position, no obstacles, the robot would succeed. But if the cup moved an inch to the left, failure. If the lighting changed, failure. If there was a shadow the camera didn't recognize, complete failure. This is why factory robots have always worked inside cages, doing the same task in the exact same way millions of times. Any variation breaks them. This approach could never work in a human home. Your kitchen is chaos. Dishes are in different places every day. Lighting changes from morning to night. Your kid left a toy on the counter. A traditional robot would be paralyzed. Enter what engineers are calling end-to-end learning, though it's picked up a more colorful nickname in the AI labs, vibe coding. Here's how it works. Instead of writing code, you demonstrate the task. A human operator wears a VR headset and motion tracking gloves that control the robot like a puppet. Want to teach it to fold a towel? You fold 500 towels. Want it to load a dishwasher? You load 1,000 dishes. But here's the key. You don't do it the same way every time. You do it in different kitchens, with different lighting, with different sized towels and different types of dishes. You introduce variation deliberately, bump the table, shift objects mid-task, work around obstacles. You're not teaching the robot the way to fold a towel. You're teaching it the concept of folding. The robot's neural network watches all of this and does something remarkable. It doesn't memorize the movements. It learns the intent. It builds an understanding of what folded means, what clean dish means, what obstacle means. It learns to perceive the world, depth, texture, object relationships, spatial reasoning, and then generates actions in real time based on what it sees. This is why 2026 robots can handle what engineers call unstructured environments. Your messy living room, a construction site with debris everywhere, a hospital hallway with people walking past unpredictably. They aren't following a script anymore. They're understanding the situation and adapting. Boston Dynamics trained their new Atlas using this method with thousands of hours of human demonstrations in dozens of different factory settings. 1X trained Neo by having operators work in real homes, not labs designed to look like homes, but actual lived-in apartments with pets and kids and clutter. And Tesla? They are training Optimus on their own factory floor, where the task changes every day depending on which car model is being built and which parts suppliers delivered on time. The robot learns to be flexible, not just precise. This is the breakthrough. Not better motors, not stronger materials, but a fundamental shift from programming robots to teaching them the way you teach a human apprentice, through demonstration, repetition, and exposure to real-world chaos. But there's still one problem that no amount of clever AI can solve, and it's the reason you don't see these robots everywhere yet. So we've solved the brain. We've taught robots to perceive, adapt, and learn like humans. But there's a brutal physical constraint that threatens to kill this entire revolution before it starts: power. A humanoid robot isn't like your laptop or your phone. It's not running a few chips and a screen. It's operating dozens of electric motors simultaneously: shoulders, elbows, wrists, fingers, hips, knees, ankles. Every movement, every adjustment, every moment of balance requires continuous power draw across the entire body. And here's the problem. Current lithium-ion batteries, the same technology in your smartphone, can't handle it. Under normal household operation, a robot like Nia running on standard batteries would last maybe 90 minutes before needing a recharge. Atlas doing heavy factory work under 2 hours. That's not a product, that's a very expensive demonstration unit that spends most of its time plugged into a wall. Think about what that means economically. If you're replacing a human worker who works an 8-hour shift, but your robot dies after 90 minutes, you'd need 5 robots to cover 1 shift, plus the downtime for charging rotations. The math doesn't work. The business case collapses. This is why despite all the AI breakthroughs, despite all the mechanical improvements, you couldn't buy a useful humanoid robot in 2024 or 2025. The battery technology simply wasn't there. But January 2026 changed that equation. Researchers at Stanford, working alongside companies like Geely and QuantumScape, just announced a breakthrough in solid-state battery technology. Now, you've probably heard the term solid-state battery thrown around for years as vaporware, always 5 years away, never actually shipping. But this time it's different, and here's why. Traditional lithium-ion batteries use a liquid electrolyte to move ions between the positive and negative terminals. It works, but it's inefficient, it's heavy, and it's dangerous. That liquid can catch fire under the right conditions. Solid-state batteries replace that liquid with a solid ceramic or polymer electrolyte. The advantage? Energy density. A solid-state battery can store 50% more energy in the same physical space. For a smartphone, that's nice. For a humanoid robot, that's the difference between being useless and being revolutionary. But solid-state batteries have had one critical flaw for decades. They crack. Every time you charge and discharge, the materials expand and contract. After a few dozen cycles, microscopic cracks form in the solid electrolyte. Those cracks create resistance, reduce performance, and eventually the battery fails completely. The January 2026 breakthrough is a new silver-nanoscale coating developed at Stanford. This coating acts like a flexible barrier that absorbs the expansion and contraction stress, preventing those fatal cracks from forming. Early testing shows these batteries can handle over 6,000 charge cycles without significant degradation. For robots, this is existential. We're now looking at batteries that can power a humanoid robot for 8 to 10 hours of continuous operation, a full work shift. And because the batteries don't degrade quickly, a single robot could operate reliably for 5 to 7 years before needing a battery replacement. Let's put that in economic terms. A $20,000 robot that can work 10-hour days, 6 days a week for 5 years is providing roughly 15,000 hours of labor. That works out to about $1.30 per hour, not counting electricity, which is negligible. Compare that to minimum wage in California, $16 per hour. The cost advantage is staggering. Companies are racing to scale this technology. Tesla is reportedly building a dedicated solid-state production line for Optimus. 1X has partnered with Norwegian battery manufacturer Freyr to secure supply. Boston Dynamics is working with CATL, the world's largest battery producer. But here's the catch. These batteries are still expensive to manufacture. Right now, a solid-state battery pack for a humanoid robot costs about $8,000, nearly half the target price of the entire robot. The technology works, but it needs to scale by a factor of 10 to make economic sense at mass production levels. That's the race we're in right now. Not just building smarter robots, but building cheaper power sources. Because without a solution to the battery barrier, even the smartest robot in the world is just a very expensive paperweight. And that brings us to the question nobody wants to ask out loud. What happens when the technology does scale? So let's talk about what nobody wants to say out loud. What happens when a robot costs less than a year's salary but works for a decade? The math is simple and terrifying. A $20,000 robot working 10-hour days, 6 days a week provides about 3,000 hours of labor per year. Over 5 years, that's 15,000 hours for a one-time cost of $20,000, roughly $1.30 per hour. Add electricity and maintenance, maybe you're at $2 per hour. Compare that to a human worker at $16 per hour, plus benefits, plus payroll taxes, plus sick days, plus training costs. The economic gap isn't close, it's a chasm. We're already seeing the early deployments: robot security patrols in Singapore, autonomous forklifts in Amazon warehouses, delivery robots navigating college campuses. But these are controlled, limited use cases. 2026 is the year this moves from experimental to economically inevitable. And here's the critical question: who owns the robots? If humanoid robots become as affordable as used cars, we could see distributed ownership. Small businesses buy one or two, families own a helper, independent contractors lease them for specific jobs. This is the optimistic scenario: automation as a tool that increases productivity for everyone. But there's another path. If the technology stays expensive or gets locked behind patents and supply chains, we could see concentration. A few megacorporations own fleets of thousands. They lease robot labor to businesses that can't afford to buy. Wealth and power consolidate even further. Instead of democratizing productivity, we create a new form of capital inequality, where those who own the robots control the economy. History tells us automation creates new jobs while eliminating old ones. The Industrial Revolution destroyed farming jobs but created factory jobs. Computers eliminated typing pools but created software engineers. But history has never seen automation with general intelligence. A robot that can learn any task is fundamentally different from a machine that does one thing very well. We don't know what happens next. We don't know if new jobs emerge fast enough. We don't know if society adapts or fractures. But we do know this: the robots aren't coming, they're already here. The question isn't if, it's how fast and who benefits. So where does this leave us? 2026 isn't the year robots arrive, it's the year they become real. Neo is folding laundry in Norwegian homes. Atlas is working 10-hour shifts in factories. Optimus is building cars inside Tesla's own plants. The technology works. The economics work. What happens next is up to us. Would you let a robot into your home? Would you work alongside one? Would you trust one with tasks that matter? These aren't hypothetical questions anymore. The age of physical AI is here, and it's moving faster than anyone expected. If you want to stay ahead of the biggest technological shift since the smartphone, like, subscribe, and share. More deep dives coming soon. This has been SynthCosmos. Thanks for watching.